got 600 nanometer light on a double slit setup. And the separation of the slits is 0.2 millimeters. The screen is a meter away. And they start to question us. Let's say we're going to set, for the intensity of light on the screen, we're going to set the origin of the y-axis on sort of the optical axis through the middle of the slits. So question A is how far are the m equal 1 fringes from the center? So how high are m equals 1 fringes? So let's see, what does that question mean? So fringes means the maxima in the interference pattern. So there's always one at the center, right? So we can draw one like this, and then it just kind of goes, it's actually kind of like a cosine squared pattern like that. So this would be, the middle is like m equals 0, because the two rays we would draw, or the two waves we would draw from each slit to there, go the same path. So there's no difference in the distance they went. So the m equals 1 refers to this one. And you might call this one the m equals minus 1 because it's below 0 on the y-axis. But really they're both the same idea. So what we do is we say, what if we had the light from this little wavelet going there and the light from this little wavelet going there, like that. The key is that that is a maximum if the difference in their path is equal to one wave, right? So we draw this line straight down, perpendicular, and we ask ourselves this distance. Is that a wave to make them back in phase? Is it two waves to make them in phase? Is it half a wave to make them out of phase, etc.? Okay, so we set it up. To solve it, though, you got to think about an angle. You got to think about the angle of these waves with respect to the horizontal. That looks like the angle is really different, but that's because I've drawn it so close. In reality, this is 0.2 millimeters. This is a meter. So really the angle of this wave with respect to the horizontal and this with respect to the horizontal are all basically the same. So I'll go ahead and just draw it here and call it theta. And then if you go through some geometry, you find out that this is also theta. So if we imagine a right triangle right here, we have one angle of the right triangle, where there's the right angle. And we know this side of the triangle is A, and this is the side we want, because this is where we need to fit in a wave. One wave in here, and then they will continue in constructive interference. All right, so what is that? What is that side? Well, we have the hypotenuse A, so it's A sine theta. Sine of theta is opposite over hypotenuse. So we say that A sine theta needs to be equal to 1, m equals 1 lambda. And I think that's, what do we do with that information? Oh yeah, then we solve for theta. So we say 0.2 millimeters sine theta equals 1 times lambda. If I wrote it in millimeters, it would be 0.0006. Yeah. Right, so you solve that, and you get that the angle is 0.172 degrees. If you're working in degrees. But that wasn't the question. The question was, how high does this occur above 0 and how far below 0? So then we just have to think of this little triangle again, and I'll kind of draw it again at a steeper angle so maybe it looks like it makes a little more sense. There's the optical axis, and here is this really small angle, 0.172 degrees, and this is where that first m equals 1 maximum occurs. We know we have 1 meter here, and we want that height, y, m equals 1. Well, let's see. So it must be that the tangent of this angle is opposite over adjacent. So we say tangent of 0.172 degrees equals opposite, that's what we're looking for, over, I'm sorry, we have the hypotenuse. It's the sine. Why did I say that? Oh, no, I'm fine. The tangent of 0.172 degrees is the opposite y over the adjacent 1 meter. There we go. Y, if you solve that, is 3 millimeters. Right? So y is 3 millimeters up here and negative 3 millimeters down there. Part A. Part A was only about interference and nothing about diffraction. So now let's look at part B. It's one of these tricky ones where you combine interference and diffraction. All right, so part B says you see 7 fringes under the central maximum. And then basically the question is, how wide are the slits? So you can maybe imagine how this question makes sense. The spacing is already set, the spacing of the fringes, that's the interference maximum. The width of the slit sets this pattern, this central maximum, this diffraction pattern. So remember, diffraction pattern looks like this. If we draw one, it's this big, usually broad central maximum, like that. And that's really all we worry about in this class, is the width of the central maximum. We don't worry about the later ones. So if you have this pattern happening and this pattern happening, you end up multiplying them to get the answer. So underneath this pattern, it's sort of the real pattern that looks kind of like this. You fit some of these interference maxima inside. All right. So we've been told 7 fringes fit. So what you're trying to figure out is, where does the interference pattern hit the central maximum's edge? That's really what you're trying to figure out. So the central maximum goes down and it stops here at the point where you have deconstructive or deconstructive interference from the diffraction pattern. So this point occurs for a diffraction at, I used A there, so the width of the slit is D, at D sine theta. How much did I move this? At D sine theta equals the order 1, because this is the first minimum, 1 times lambda. D sine theta equals lambda. It's not lambda over 2 because of weird stuff about diffraction. So that's where the first minimum hits. That would be the angle at which you see that first minimum. Now we could also think about, where does the interference maximum occur? We got to think, which one do we want to land right there? Right? So if they said you have 7, let's think, what does that mean? You always have 1 in the middle. That means it leaves you with 6. But you have the same number on each side. So you must have 3 over here, and 1 in the middle. So what I drew here is 5. And the problem, we have 7. So that does not mean that the third maximum sits there, because the third maximum gets taken out. What it means is the fourth maximum might sit there. So we could write the interference condition that puts the fourth maximum in the same place as the interference or the diffraction minimum. So let's see, what is that? That's A sine theta equals 4 times lambda. So it's basically the same equation we used before. We want this A sine theta to be 4 waves, because that's the fourth peak. We're putting it right there. If the fourth peak is missing because of diffraction, then the other 3 will be there, and we'll have 7. So it's really this equation. What we're doing is we're setting these thetas equal. This was the diffraction theta. This was the interference angle, but we're saying let's make them the same. Theta interference equals theta diffraction. So they're both sines, so all we got to do is say 4 lambda over A equals lambda over D. And it's the same lambda, right? So if we're solving for D, the width of the slit, which I never really labeled, but this is D, then it is A over 4. Right, because that goes over there, yeah. A over 4, it is 50 microns. This was 200 microns. So you divide by 4, you get 50. That is an answer to this problem. That's not the final answer, or that's not the entire answer, because the slits could be a little bit wider, right? If the slits were a little bit wider, what would happen if we took out the fourth maximum and made it so it's a little bit wider? This zero that the diffraction causes would start to move this way, but it wouldn't immediately take out the maximum that we need. Right? So instead of putting, let's pretend this was the fourth one we were taking out. Instead of putting the diffraction zero here, we could put it here. Another mathematical place you could put it would be on the minimum that comes after the third maximum. If you put it there, you would still see that maximum. It would still be a fringe under the central maximum. So you could also set this up and say another option would be to say, let's see, A sine theta equals 3.5 lambda. A sine theta I equals 3.5 lambda. And the D part would be the same. We're looking at the diffraction minimum. D sine theta D equals lambda. And then set theta I equals theta D, and you end up getting equals 57 microns. Right, you make it a little bit bigger, you bring it in a little bit more, you put it here, you put it here. Where you can't put it, you may have calculated, if you calculated, oh, I need to hit number 3, I need 3 in there, you can't put it on 3, right? Because then you've taken number 3 out by putting the diffraction minimum on it. You need number 3 still in there. So you could kind of get a range from 50 microns to 57. It could be even a little bit bigger, right? You could bring it in a little bit, but if you get much closer, you're starting to get too close to that interference maximum that you need. Think about that. Let's see, part C. The question for part C was, if the slits come together, what happens to the pattern? Okay, well, let's see. If the slits come together, we could just go anywhere where we see our interference equation. And if the slits come together, this number gets smaller. And therefore, if the wavelength is constant and we're tracking one of the peaks, like 1 or 2, that's constant. So if this gets smaller, this has to get bigger. So the angle gets bigger, so the pattern expands. The question was a little vague about whether or not the widths also got smaller, right? You could bring them together without contracting the widths. So if you kept the width the same and brought the slits closer together, the diffraction envelope would stay the same, and the interference fringes would spread out. If you brought them close together and the widths got smaller, then the whole pattern would spread.